Hello, physics students. Um, we're working on fluids and buoyant force this week, and I have tried countless times to make a video that kind of summarizes everything you need to know and to keep it under 15 minutes, and I cannot do it. So this slideshow will be posted on Canvas here this morning, Monday morning, but um, I'm going to march you through how to solve an equation, how to solve a problem calculating a buoyant force in a fluid. So a buoyant force is, let's just kind of race back to a definition. Um, this A buoyant force is what keeps objects afloat or makes them feel lighter underwater. So this person can do push-ups aplenty underwater because he feels lighter while he's underwater. This person can lift up a big old barbell with a big mass on it, and it's easier for him to do that underwater because of the buoyant force. So gravity still acts on this guy doing push-ups and still pulls just as hard. Gravity still acts on this barbell and still pulls just as hard, but something else is pushing upward, and that something else is called the buoyant force, right? So there's Archimedes Principle is this equation that we use to calculate the buoyant force, and we wanted to calculate how much lighter does something feel, or well, several things we could calculate with it. And so here's the Archimedes Principle just in general. If you have some mass hanging out here in air and you immerse that in water, a certain amount of water will be pushed out, it will be displaced. The mass of that displaced water kind of offsets the mass of the original object. And so underwater, if the mass of water that got pushed away or displaced was 2 kilograms, it will be as if this mass now is only 3 kilograms. Okay, so it started out as 5, but you can kind of offset these 2 kilograms, and so you have an effective mass or an apparent mass of 3 kilograms. We're talking about mass and force because the buoyant force is not 2 kilograms here. The buoyant force is a force, not a mass, so it's force times an acceleration of gravity. But we'll get there. Okay, so the buoyant force equals the force of gravity on the displaced fluid, and the force of gravity on the displaced fluid is the mass of the fluid times gravity, 9.81 meters per second squared. The magnitude of the buoyant force equals the weight of the fluid displaced. Weight is not mass. So the magnitude of the buoyant force equals the mass of the water times the gravity pulling downward on it. All right, so a floating object, the buoyant force equals the object's weight. So think about the Titanic as it's floating along through the North Pacific, or North Atlantic, excuse me. It has a force of gravity pulling downward on it, but also had a force of buoyancy, the buoyant force pushing upward on it. And those two were in perfect equilibrium, which meant the Titanic didn't sink and it didn't fly off into space. Something intervened, and eventually the buoyant force did not match the force of gravity. The force of gravity still was pulling down just as hard as it always has, but the buoyant force couldn't keep up with it anymore because of a big old hole in the hull. And so eventually the buoyant force couldn't counteract the force of gravity, and the Titanic sank. But as long as they're equal, an object will float. If the buoyant force is less, the object will sink to the bottom of whatever, the pool or the cup or the Atlantic Ocean, whatever it's floating in. Never will you see an instance where the buoyant force is greater than the force of gravity acting on an object. It'll never be a buoyant force that actually makes the Titanic float off into space. It doesn't happen that way. Right. So I'm racing through this because the slideshow is posted on Canvas, but you need to be able to kind of get to the point where we're going to be able to solve a problem. So here's what I want to get to. You can just trust me on this. We are building this equation here. Here's the equation we want to write down or know. We're going to use that this week. The force of gravity, we're setting up a little proportion. Okay, the force of gravity of an object divided by the buoyant force equals the density of the object. This P is a Greek letter rho So the force of gravity on an object divided by the buoyant force equals the density of the object divided by the density of the fluid. That's what this equation means. So make note of that relationship there. That's going to be important. It'll be important for this next problem, which is Archimedes and the Golden Crown. So there are, the legend is that Archimedes, this Greek mathematician, was tasked with calculating whether or not a blacksmith had used a right amount of gold in building a crown. So the king of Syracuse, Huron, had given a blacksmith a certain quantity of gold and said, hey, build me a crown, man, and use all this gold to do it. And then when he received the golden crown back, he wasn't sure that it was all there, that it was really all gold. And so he needed to figure out how he could do that. And the Archimedes' solution came to him as he was climbing into a bath, probably not a bathtub, but a Greek bath, whatever that looked like. And he realized that as he got in, as Archimedes stepped into water, he displaced some volume of water, which meant he could calculate his own volume, which meant he could calculate his own density if he submerged himself. And he realized that that was the solution to the problem of the golden crown, that he would be able to find out if that crown had the right density or not. And that caused him to leap into out of the bath and cry Eureka, which means I found it in Greek, and then run through the streets of Syracuse naked to go solve his problem. Okay, so we're going to do a similar problem here, and we are going to assume that we are given a crown that has a force of gravity, or a weight, of 7.84 newtons. When we put that crown underwater, that crown has an apparent weight of 6.86 newtons. So that means there's a buoyant force of 7.84 newtons minus 6.86 newtons. The buoyant force is 0.98 newtons. That's important. The other thing that we know is the density of water. Density of the fluid equals the density of water equals 1 times 10 to the third kilograms per cubic meter. It's very heavy, it seems. It's hard to believe that water has that much mass, but it does. So we're tasked with finding the density of the object, density of the crown. Here's how we're going to do that. Here's our equation that we know and love. The force of gravity of the object divided by the buoyant force equals the density of the object divided by the density of the fluid. We're going to do some algebra on here and solve for density of the object. So it's density of the fluid times the force of gravity on the object divided by the force of the buoyant force. And when we plug those numbers in, density of the water times the force of gravity on the object divided by the buoyant force, we're going to come up with an answer of the density of the object is 8.0 times 10 to the third kilograms per cubic meter. That's the density of our golden crown. So in this problem, this is not the density of gold. If this were actually a crown made of solid gold, that density should be like 19.3 times 10 to the third kilograms per cubic meter. So in our story, like in Archimedes' original story, the blacksmith cheated us, or cheated to Huron, the king of Syracuse. At any rate, that's how these problems are done. I'm going to post up 5 little sample problems on Canvas here as an assignment to work on this week. And there are 2 opportunities. On Tuesday and Thursday, there will be a chance to kind of do some face-to-face time. Actually, I want you to pick a day, sign in. We're going to do a log in and watch and zoom in with this meeting. And the meeting will be a chance for me to just check off that you're still alive, and then also for you to ask me questions about this buoyant force problems. Okay? Go be awesome, and may the 4th be with you.